Okay, let me begin. Okay. Why do I feel like it's smaller this time? Really? Oh, there we go. Okay. There we go. So, last time we started talking about the syntax and semantics of, yeah, it's always sideways for someone. I don't know what to do about that. Because it's not sideways for everyone else usually. Correct me if I'm mistaken. Yeah. So I really don't know what's going on with that. Because my lack. I think so. I mean, I guess, are you on a computer? I mean, okay, that's weird, because on my computer it's fine. Discord. Let's. Oh shit! What did I do? Yeah, that's probably the best idea. The best advice is to try to refresh. In the meanwhile, I'll just quickly go through what we did last time. Well, not through everything, but we talked about. We were talking about first order logic. Right. We talked about syntax and semantics. So right, we had mathematical structures, right, which were like sort of a generalization of things that have operations and relations and constants, whatnot. First order formulas, which were stuff like for all x there exists y, x plus y is less than, let's say, I don't know, greater than or equal to x, stuff like that. I don't know, random stuff that I'm throwing out here. And what we proved a few things about semantics, and that took us some time. Nothing super interesting. This is going to be the lecture where we actually prove some interesting stuff. But first we need to continue with semantics, some stuff that we weren't able to get to last lecture, which is really just formalizations of what we're going to start with is our substitutions, which we can sort of understand intuitively in our head, and it's a lot harder to formalize. So this is like probably my least favorite part of first order logic. So bear with me. But okay. A global substitution is a function sigma from our variables to terms, to our set of terms t. So then we can obviously expand this. We can expand this to sigma from formulas to formulas. Well, actually, let's start by expanding this from terms to terms by so first we have to start with prime terms, right, or atomic terms, but those are already defined. So for x, so for a variable to substitute it as x, this is already defined. For a variable. Why is it already defined? Because sigma is a function from the set of variables to terms. And then for constants, we just define it to keep constants constant. Because obviously, if I'm changing a variable with something, it's not going to affect the constant. Now, for a term, compound term, ft1 through ftn, sigma, that is going to be f of t. We have to be careful about parentheses here, but f of t1 sigma through tn sigma. So for example, if I have a variable, if I have a global substitution x, which maps sigma, which maps x, let's say, to x plus 1, and y to x, then x plus y, right, here I have to put really parentheses here, gets mapped to x plus 1 plus x, right? And so on. So it really is substitution here. That's pretty much all it does. And we can extend this to formulas. We extend sigma from formulas to formulas, right? As follows. So we have to start with prime formulas. So for for an equation, right, you start with t equals s. The substitution of that is just going to be t, the substitution of t, equals the substitution of s, right? Yeah. For if I have the relation of r of t bar, that gets mapped to r of t bar sigma. Right, so here really, right, that's t1 sigma through tn sigma. And 3, alpha and beta, the substitution of that is just alpha, the substitution of alpha, and the conjunction of that with the substitution of beta. And finally, for all x alpha, the substitution of that is just for all x alpha sigma prime. Where sigma prime is equal of y is equal to sigma of y when y is not equal to x, and x when y is equal to x. So what it does is this quantifier sort of stops substitution. So if I have sigma which maps x to y, then let's say for all x is equal to x, the substitution of that will just be for all x equals to x. It doesn't change it. Because what we want to do here with substitutions is we want to substitute all the free variables. And that's exactly what this does. It substitutes all the free variables with their substitution, but keeps bound variables or bound occurrences constant. One sec. Let me just make sure I'm recording this. Okay. Oh, and also we also my bad. We also have the substitution of negation is just negation, right? The substitution of alpha negated. Okay. If sigma maps only x1 to t1 through xn to tn, right? So and it keeps all other variables, and it keeps all other variables constant, then we write sigma is equal to t1 through tn over x1 through xn. So, or t bar over x bar. Okay, and so it looks like a fraction, right? And this is called a simultaneous substitution. And if n is equal to 1, then this is just a simple substitution. So all simultaneous substitutions can be written as a composition of simple substitutions, but it's important to notice that t1 through tn over x1 through xn is not the same as t1 over x1 composed with t2 over x2 and so on through tn over xn. Right, and this is kind of where you start to notice that substitutions are a little annoying. The reason why this is because let us take t1 is equal to x1 and is equal to x2, sorry, and t2 is equal to x1. Then t1 t2 over x1 x1 over x2 is equal to x2 over x1 x2 x1 over x1 x2, right? So it swaps x1 and x2. But t1 over x1 and t2 over x2 is equal to x2 over x1, x1 over x2. And what that does is it swaps x1 with x2 and then x2 with x1. So x1 stays the same, right? Because we go x1 to x2, then back to x1. And x2 goes from x2 to x1. So x2 goes to x1. So we have that x1 and x2 are both mapped to x1, as opposed to being swapped. So composition doesn't really work here. It doesn't really, it's not as nice as you would hope. But if you have another variable, let's say I have t1, t2 over x1, x2, I can write this as t1 over x2, right? I can introduce another variable. Here, let's start. So, yeah, sorry. I can go like t2 y is, x2 is swapped with y, and then I go x1 is swapped with y, let's say, then x2 is swapped with that, and then y is swapped with t1, sorry. Right, or something like that. Pretty much, basically, you substitute in another variable y, which does not occur in the variables of t1 or t2, and you can play around with that. But that's not really important. But that's less important. Another thing to notice about why substitutions are not all that amazing by themselves, right? You need some restrictions on them. Is that if m satisfies for all x phi, this does not mean that m satisfies phi of the simple substitution t over x. Now, we would want this, sort of, right? Because another way of writing this is if m satisfies phi for all x phi of x, then that means that m satisfies phi of t, right? We're saying that I can input any t that I want, and phi holds, because phi holds for every x. But this is not true. Why is this not true in general? Take phi to equal there exists y such that x does not equal y. So for all x phi is equal to for all x, there exists a y such that x does not equal y. Which is true when m has more than two elements, at least two elements. But now let us take But notice, let's take t to equal y. Then phi of t over x of t over x is equal to phi of y over x, which is equal to exists y such that y does not equal y. And certainly that is a contradiction. And for all x, phi is also a that's a contradiction. So m does not satisfy phi of t over x. So we have to have this. So we have to kind of look at this example and figure out where we went wrong. And where we went wrong is the fact that phi and this substitution, phi and t over x, makes a free occurrence a bound one. Right? So we took a free occurrence, which was this x, and we made it bound. So what we can say is that if a substitution does not do this, then it is collision-free. We can define collision-free that way. Though that is a recursive definition that's kind of annoying to play, that's a little harder to play with, but it is more natural than the definition we are going to use, which is a little more crude. The definition we are going to use is phi and t over x are collision-free if y is not in the bound phi for y in var t minus x. So basically, if for all the variables, so if where bound phi is the set of all y such that for all y occurs in phi. So we're saying that for any bound variable in phi, it doesn't exist in what we are substituting in. So what we have before is not collision free because we have y is in bound phi and y is also in the variables of y minus x, which is just the variables of y, which is y. So we have that's not collision free, and that's why we kind of get our issues. But collision free substitutions are very fun to play with, very easy to play with, and they are what we want. And in general, phi and sigma are collision free if phi and t and x sigma over x are collision free for all variables x. So if a global substitution is collision free, given that every simple substitution over it is collision free. Okay. Now let's prove a nice lemma about it. Okay. Okay. Let M be a model and sigma a substitution. We define M sigma to be a model over the same domain but with a different valuation, where x w sigma is equal to, here, let's write it this way. W sigma of x is equal to sigma of x of m, right? Which is equal to the valuation of sigma x. Oh no, I can't write it like that really, but okay. In other words, x of m sigma is equal to x of sigma of sigma of m. Okay. Basically what this means is that m of sigma, what it does is it first substitutes x, and then it takes whatever that value is relative to m. So for example, if m is equal to the natural numbers and sigma maps x to y and y to, let's say, y plus 1, and m is the natural numbers with evaluation w, which maps y to 3, then it will x of m sigma is equal to x of sigma m, which is just going to be y of m, which is going to be 3. And x and y of m sigma is going to be equal to y sigma m, which is going to be y plus 1m, which is going to be 4. Okay, and that's what our new structure is. Okay. Now, what we want to show, why we define this is because I want to prove the following. So for all phi and sigma, such that phi and sigma are collision free, m satisfies the substitution of phi if and only if m sigma satisfies phi. And let's prove this for prime formulas. I'm going to skip the rest of the proof. Is a little, it's not trivial, but it's not super hard. Maybe I'll prove it. Yeah, I'll prove it. Okay. So m satisfies t equals s sigma if and only if m satisfies. Also notice that t of m sigma is equal to t sigma of m for all terms t. For all terms. Sorry about that. It's true for variables. It's gonna, you just do term induction on it. It's not that hard to prove. Okay, so that's t sigma. This is if and only if m satisfies t sigma is equal to s sigma, which is if and only if t sigma of m satisfies s sigma of m, which is if and only if t m sigma is equal to s m sigma. Okay. And so, which is obviously, right, if and only if m sigma satisfies t equals s. And then for prime formulas, which are of the form r t bar, it's similarly proven. And for alpha and beta, the conjunctions and negations are trivial. So all that remains are quantified formulas. So okay, so m satisfies for all x alpha sigma if and only if m satisfies for all x alpha sigma for alpha tau. Say where tau of y is equal to sigma of y when y is not equal to x, and x when y is equal to x. Okay. This is if and only if m a of x satisfies alpha tau for all a in m. Or a in a, I guess, right? Over its domain. It doesn't really matter. Now, what we now know from induction is that this is if and only if max of tau satisfies alpha. Now we are going to claim that m1, which is equal to max of tau, is equal to m sigma of ax, which we'll call m2. Now you can verify that this is true, and so that this is just equivalent to m sigma of a over x satisfying alpha for all a in a, which is if and only if m sigma satisfies for all x alpha. Okay, So we've proven it, and we're great. Okay. A corollary is if phi and the simple substitution are collision-free, then 1 for all x phi, from that you can derive that phi of t bar over x bar. 2 phi of t bar over x bar implies there exists an x of phi, and 3 phi of s over x and s is equal to t implies phi of t over x if phi and t over x and phi of s over x, oh sorry, I already said that phi of t over x is collision free if phi and s over x are collision free. And the proofs you can find in the lecture notes, they're really not that hard. Okay, and notice that then we can, using substitutions, we can define the unique existential quantifier, which is there exists a unique x such that alpha, which we define to mean this is if and only if there exists an x such that for all y, phi of y over x, if and only if y is equal to x for y not in the variables of phi. So we're saying that there exists an x such that, right, so for any y satisfies phi if and only if y is x. So firstly, x does satisfy phi, and if another y satisfies phi, it's equal to x. Okay. Now let's talk about, now that we've gotten that down, let's talk about elementary equivalence. Okay. Definition: alpha and beta are elementarily equivalent, denoted alpha is equivalent to beta if m satisfies alpha, if and only if m satisfies beta for all models m. Okay, so for example, t equals s is going to be equivalent to s equals t, right? And so on. This can also be written as this is equivalently, alpha if and only if beta is a tautology. Alpha implies beta and beta implies alpha, etc. Okay. Now notice that L forms an algebra over the signature conjunction, disjunction, conjunction, disjunction, and for all x, for x in variables. So we can talk about congruences on this, on L. So, right, we can discuss congruences, right? Because it in and of itself is a structure. So a congruence is one such that when alpha is congruent to alpha 1 is congruent to alpha 2 and beta 1 is congruent to beta 2, then that means that alpha 1 and beta 1 is congruent to alpha 2 and beta 2. Sorry, not disjunction, but negation. What did I write here? Yeah, okay. Negation of alpha 1 is congruent to the negation of alpha 2. And for all x, alpha 1 is congruent to for all x, alpha 2. Okay, so it's a congruence, so we have this. it's easily verified that equivalence, elementary equivalence, is a congruence. So we have the following theorem, or lemma, the replacement lemma, which says that if we have an incongruence over L, and alpha is congruent to alpha prime, and phi is some formula in L. If phi prime is obtained by substituting alpha prime for one or more occurrences of alpha in phi, then phi is congruent to phi prime. Okay, so like for example, if I have alpha and beta or gamma, and alpha is congruent to alpha prime, then this is going to be congruent to alpha prime and beta or gamma. For example, stuff like that. And the proof, which we will gloss over, is by formula induction. Okay. Okay. Definition. Let A be an L structure, then phi, let's say alpha and beta are equivalent modulo A, written alpha is equivalent modulo A to beta, if and only if alpha W satisfies A and W satisfies alpha, if and only if A and W satisfies beta for all valuations W. Okay. If K, now notice that a congruence of an intersection of a family of congruences is also going to be a congruence. So if K is a class of L structures, equivalence modulo K, which is just going to be the intersection of all the equivalences modulo A of elements in K, is also a congruence. Okay. Oh, and this is equivalent to saying A satisfies alpha if and only if beta. Okay. Notice that equivalence, elementary equivalence, is a subcongruence of equivalence modulo A, and so on. Okay. Notice that here's some equivalences. For all x, alpha and beta is equivalent to for all x alpha and for all x beta, and there exists x alpha or beta is equivalent to there exists x alpha or there exists x beta. Similarly, for all x, for all y alpha is equivalent to for all y, for all x alpha, and there exists x, there exists y alpha is equivalent to there exists y, exists x alpha. If x does not occur free in beta, then we also have for all x alpha or beta is equivalent to for all x alpha or beta. Okay, and there exists x alpha and beta is equivalent to there exists x alpha and beta, and so on. right? For maybe here's an important one. I guess not really. For all x, beta is equivalent to beta, which is equivalent to exists x beta. So you can, if x doesn't occur free in beta, you can just get rid of the quantifier in front of it. Okay. Now here's another one. For all x alpha is equivalent to for all y alpha of y over x when this is collision free. And similarly, exists x is equivalent to exists y alpha y over x when that's collision free as well. And the reason for that is because, right, or when y is not in the variables of alpha, that makes it simpler, and so on. You can prove this pretty easily. It's like a one-liner. Okay. Okay. Now, a definition. A prenex normal form is a formula of the form q1 x1 through qn xn phi, where phi is quantifier free and qi is a quantifier and for all or exists. Okay. So theorem, here's the theorem why we care about prenex normal forms. The PNF theorem. Every formula is equivalent elementarily to a prenex normal form. Now the proof of this is basically you can just sort of inductively shift over quantifiers to the left. So right, the negation of for all x alpha is just exists x negation alpha. That's right, those are elementarily equivalent. Similarly, negation of exists x alpha is for all x negation alpha, and beta and q x alpha is equivalent to q y beta and alpha of y over x, and similar for for disjunction. And so basically you see that at each point we're shifting over the quantifier. Right, we're shifting it over to the left. So here we're shifting a quantifier to the left and to the left, and you can do that inductively, and you get that in the end you're left with a prenex normal form with a quantifier free formula in the middle. And obviously that quantifier free formula can be in DNF or CNF. Yeah. Okay. Here, obviously, y is not in the variables for alpha or beta. Okay. Okay, now let's talk about logical consequence. Right before, I think we defined this last lecture, but we wrote alpha is a logical consequence of x if and only if, when m satisfies x, it also satisfies alpha. So for example, here's some examples. One, when x satisfies for all x alpha, implies alpha t over x for alpha t over x collision free. And 2, x satisfies alpha s over x, s is equal to t, alpha x satisfies alpha t over x for alpha tx and sx collision free. 3, x and beta satisfies alpha, means that x and for all x beta satisfies alpha 4, yeah, pretty much similar, whatever, so on and so on. It's not very important right now what this list of stuff is, but you see that we have this sort of these sort of rules. And now using these rules as a guideline, we can get back to our friend Gensen calculi. And the idea again is to prove the compactness theorem, but this time for first order logic, which is the same thing. It's the same statement as in propositional logic. It says that X is going to be satisfiable if and only if every finite subset of X is satisfiable. And also the finiteness theorem, which is that X implies beta, implies phi, if and only if some finite subset of X implies phi. Okay, so our Gensen calculus is going to have the following rules. So we start with initial sequent, right, which is premiseless, and it just says alpha implies alpha, or from alpha you can derive alpha. We also have the equational sequent. Sorry, that I was trying to for a second I was trying to remember what I called it, TES, which just says that t is equal to t for all terms t. And then we have the monotonicity rule, which you all know, which is if alpha derives from x, then alpha derives from x prime for x prime a superset of x. Then we have and 1 and 2, negation 1, negation 2, as before. Right, this one is like if alpha and if both alpha and beta are can be derived from x, then their conjunction can be, and vice versa. If x implies alpha and the negation of alpha, then x implies beta, and if x and alpha implies beta, and x and the negation of alpha implies beta, then x implies beta. Right, that's what all these things are. And now we want to add some more. This is enough for propositional logic, but it's not enough for first order logic, because we need to deal with quantifiers. So we're going to have for all 1, which is if x satisfies for all x alpha, then x, not satisfies, but implies alpha of t over x when alpha and t over x are collision free. For all 2, which says that if x satisfies alpha and y over x, then x implies, sorry I keep on saying satisfies, for all x alpha for y not in the free x or the variables alpha. And finally we have equals, the equals rule, which is if x satisfies s is equal to t and alpha s over x, then x satisfies alpha t over x. Okay. You can also do you can do induction, like you can do Gensen rule induction or whatever, and as in propositional logic, and using that we can prove the following. Suppose L's signature is sigma, then if x implies alpha over L, then there exists an x naught, which is a finite subset of x, and a finite subsignature of sigma, such that x naught implies L sigma naught alpha. Right, so basically what this says is it's finiteness, right? This is pretty much finiteness, but it tells us finiteness about the signature as well. You can take a finite signature and it holds in you just need a finite signature as well as a finite set, and the proof is by rule induction. And okay, you can prove the following stuff, which I'm not going to do. You can find this in the lecture notes. So if x implies s is equal to t and s is equal to t prime, then x implies t is equal to t prime. If x implies s is equal to t, then x implies t is equal to s. And if x implies t is equal to s and s is equal to t prime, then x implies t is equal to t prime. Right, none of these should be surprising. It's just that because we're dealing with syntactic things here, we have to be very careful about what we do, and not everything that makes sense is trivial. Okay. We can also prove, right, that if x implies ti is equal to ti prime, then x implies f of t1 through ti tn is equal to f of t1 through ti prime through tn. Which basically means if ti is equal to ti prime, then you can substitute it in some term, and similar for relations. Right, so here what we can write is we can generalize this. We can do this n times and say if x satisfies t bar is equal to t bar prime, then x implies f of t bar is equal to f of t bar prime. And for relations, if x implies that t bar is equal to t bar prime and f and r of t bar, then x implies r of t bar prime. Okay. Now let's talk about, we want to prove completeness. So that's what we are going to do now. Okay. Definition. X is inconsistent if x implies alpha for all formulas alpha. Otherwise, x is consistent. This is the same as saying this is equivalent to saying x being inconsistent is equivalent to saying that x satisfies some contradiction. Where for any meaningful definition of contradiction, it's equivalent to that. For us, it was there exists x such that x does not equal x, and you can show that x implies for all x, x is equal to x always. Like this can be shown, right? So this is a tautology, and so if it shows that if x implies there exists x such that x is not equal to x, these two are negations, and so by -1, negation 1, you get x is alpha, and so on. So basically, that's why this is fine, and so this, as in propositional logic, you get that that this is a fine definition of inconsistency. And as in propositional logic, you have the two C plus where x and alpha, or sorry, x implies alpha if and only if x and the negation of alpha are inconsistent, and C minus where x implies the negation of alpha if and only if x and alpha are inconsistent. So this is the same thing as in propositional logic, nothing so special here. And now let's get to another definition. Let C be a set of constants. Let LC be the language obtained by adding C to the signature of L. So pretty much I just add C to a bunch of constants to my language. Okay. Let C be a constant, X a variable, or let's say, right, let's take Z a variable, then alpha of z over c is the formula. This is just going to be the formula obtained by substituting z for c. Right, I just take c and I substitute z instead. Right, we don't need to define this formally. Not recursively at least. Formally isn't. You can do it just like naively, which is fine. Okay. Okay. So here's what our lemma. We're going to have a quick lemma, but I'm not going to prove it. You can find the proof in the lecture notes because I find these proofs kind of tedious. Suppose x implies alpha over some constant expansion of L with a single constant, then x of z over c implies, obviously, when I have here, a quick side note, let's go up. So here, if I have a set of formulas, right, I have x, and I want to, and I have the substitution of x, that's just all the substitutions of formulas in x. Right? Okay, nothing so special, sorry. I digress. So then x, the substitution of x, implies over L the substitution of alpha. And from this, proof in lecture notes. Okay. So then we get this rule for all, let's call it for all three, which says that if x implies alpha of c over x, then x implies for all x of alpha, where c is not in the variables of x or alpha. Hey, Smay. Okay, so suppose why is this true? Suppose x implies alpha of c over x. By finiteness, x is finite, and by the previous lemma, taking LC to be equal to L, we take y not in x and alpha, right? Because x is finite, we can take a y that's not in x. For all but a finite number of z's. So because x is finite, I can find a y that's not in x and not in alpha, and then using that y, I have that x is equal to x of y over z, y over c, right? Because c is not in x. C is not in the variables, but it doesn't occur in x or alpha, which then we know implies alpha c over x, y over c. But right, because by this lemma, right? This is exactly what we have here. And this is because it's just equal to alpha of y over x. Why is this equal to alpha of y over x? Because c doesn't occur in alpha. So what I said before about composing substitutions, that's what we're doing here. And by, what was it, for all 2? Was it for all 2 or for all 1? For all 2. By for all 2, this means if x implies for all x alpha. And so we finished. Now we can also show the following lemma. which justifies our use of not our us not using subscripts on this derivability symbol is so let C be a set of constants, and for a set of formulas in L and alpha in L, X implies alpha under LC if and only if X implies alpha under L. So right, us adding these constants will not affect us proving alpha. And why is this true? This is true because we already made this comment earlier about if L is contained in L prime, etc. Okay. Okay. Okay, so for now what we're going to do is we're going to get to the actual proof of completeness. So to do this, we need to create, do some playing around. So for every variable x and formula alpha, we define a constant c of x alpha, and alpha to the power of x is going to be the formula, what is it? Not for all x alpha, and alpha cx alpha over x. Okay, so notice that the negation of alpha to the power of x is for all x, negation of alpha implies not alpha cx alpha over x. So basically, the negation of alpha to the x means that if there is a counterexample to alpha, right, if there exists an x such that the negation of alpha holds, then c sub x alpha forms a counterexample to alpha. So it in and of itself is a counterexample. Okay, nice. Okay, so and notice alpha to the x is equivalent to a contradiction whenever x does not occur free in alpha, sorry. Because if x does not occur free in alpha, then this is just equivalent to not alpha and alpha. Okay. Yeah, I have a tendency to say notice. Sorry. Okay. Okay. Now our lemma. That L be a signature. Let's define gamma of L to be all the negations of alpha to the power of x for alpha in L and x in and x a variable. If x is consistent, so is x with gamma. Okay. So suppose not. So x and the union of gamma proves a contradiction. And then by finiteness, we have alpha 1 x1 alpha n xn in gamma such that x and alpha 1 x1 through alpha n xn proves a contradiction. Okay. Okay, and because x is consistent, n is greater than or equal to 1. So we can assume n is minimal, right? So if I take a smaller n, I like for this specific set of alpha, for alpha 1s through alpha n's, we take a smaller n, it is consistent. Okay, now basically what I'm going to do here is I'm going to reduce our n by 1. So basically what I have is, okay, let x prime be x and the union of alpha I xi for I equals 1 through n minus 1. And let x equal xn, c equal, alpha equal alpha n, and c equal cx alpha. So x prime proves alpha to the power of x, alpha to the x, right? Because basically what we have is x prime and the negation of alpha to the x proves a contradiction. So by c minus or c plus, we get this. Okay. So x prime proves for all x alpha, the negation of for all x alpha, right? If we literally look at the definition of alpha to the x, so negation of for all x alpha and alpha c to the x, but by for all 3, we get x prime proves, alpha to c to the x. For all x alpha. Right, we use for all 3 on this. So we have that x prime proves the negation of for all x alpha, and it also proves for all x alpha. But n is minimal, so x prime is consistent, which is a contradiction. Right, because we just showed that it's inconsistent. Okay. Now we're going to get to something called the Henkin construction, which is our main construction for proving what we want. For proving completeness. That basically our Gensen calculus is the same as satisfiability or derivability. So let X be a set of formulas. It is a Henkin set if it satisfies H1, which is X satisfies alpha if and only if, or X satisfies X satisfies negation of alpha if and only if alpha does not derive from X. And H2, X implies for all X alpha if and only if X implies alpha of C over X for all constants C. Okay. H1 and H3 imply H3. H1 and H2 imply H3, which is for all terms there exists a constant C such that X implies T equals C. Right? Because if X does not imply not for all X, T does not equal X. Why is this true? Because there always is going to exist an X such that T is equal to X. This, I think, was proven. Oh, yeah. So this is proven in the lecture notes. The lecture notes will be available afterward. So this is a proof in the lecture notes for x not in variables of t, and so x does prove this. So by h1, x does not prove for all x, t does not equal x. And then by h2, we have x does not prove does not prove alpha of c over x for some constant s, c. And by h1, we have x proves the negation of alpha of c over x. Why am I running alpha? Alpha is t does not equal x. So it's negation of that, which is the negation of t does not equal c, of t equals c, which is just if and only if then x implies t equals c. Sorry, that would have been easier to do from the start, from the get-go. But okay. Now, why do we care about Henkin sets? Henkin sets are basically our maximally consistent set. From propositional logic. But basically every x set of formulas is contained in a Henkin set over some constant expansion of L. So the proof of this is we're going to be using some of Zorn's lemma, a bit of everything. So we define x naught to be equal to x and L naught to be equal to L. Then define x ln plus 1 to be equal to ln with the constants of c, x, alpha, n for x in var and alpha in ln. So we're adding new constants to L sub n, where for every variable in every formula, we add another constant. And xn plus 1 is equal to xn with gamma of ln. Okay, which is obviously going to be in ln plus 1, right? Because, okay, and what we proved before is that if xn is consistent, so is the union of xn and gamma of L. And so we have that this implies that xn is consistent for all n. Okay, now we define x prime to be the union of xn's, and this is consistent by finiteness, because because it's a chain, and so if I take a union of the chain and I take a finite subset of that chain, then and if that proves a contradiction, and I take up, then there must be a finite subset of that chain that proves a contradiction. But that's all contained in one element, which is consistent, which is a contradiction. Okay. So this is consistent. Then x prime has a maximally consistent extension y. This is just using Zorn's lemma from same as propositional logic. We just take H to be the set of all consistent extensions of x prime, and then we show that every chain has an upper bound by taking the union of the chain, and we show that that's consistent because, like what I just said, is that unions of consistent chains is consistent, and so it has a consistent extension y obviously L prime to be the union of L sub n's. Okay. we claim that Y is a Henkin set. Okay, first note that if alpha is in L sub n, where n is minimal, then negation of alpha to x is in xn plus 1, right, by definition, because it contains the gamma. And so, which is a subset of x prime, which is a subset of y. So so we have that negation of alpha x is in y for all alpha in L prime, right? Or in other words, y, from that you can derive negation of alpha x. Okay, now for H1, y does not imply alpha, implies y, well, y implies the negation of alpha, implies that y does not imply alpha by consistency. And y does not imply alpha, then alpha is not in y, and since y is consistent, y is maximally consistent, y and alpha form a contradiction, which means by C plus or C minus, y implies the negation of alpha by C minus. And H2 tells us that if x implies for all x alpha, by for all 1, x implies alpha c over x for all constants. Sorry, this should be y. Okay. Now suppose y satisfies alpha c over x for all constants c. In particular, c equals c x alpha n, where alpha is in L sub n. Suppose y does not satisfy for all x alpha, then by H1, y satisfies negation of for all x alpha and alpha of c over x. So that means that y satisfies alpha to the power of x, alpha x. But we already know from here that it satisfies the negation of that. So y is inconsistent, which is a contradiction. Okay. Okay, so y is inconsistent, so y is a Henkin set. And since y is a Henkin set, so we have, and it's a maximally consistent extension of x, so we have our desired result. Now, lemma, every Henkin set y is consistent. Proof, sorry, is not that it's consistent, is satisfiable. Okay, so what we're going to do is we're going to define a congruence on the term algebra by, so two terms are congruent if and only if y says they are equal. Then this is a congruence. So since it's a congruence, it defines a quotient a quotient algebra on the term algebra. So let A be the term algebra quotiented by this congruence, and let T bar, I guess this is kind of unfortunate, but let T bar be the quotient, sorry, not the quotient class, the congruence class of T. Okay, so then basically what we're defining is we define M alpha W to be a model where firstly for prime terms we have x of M is equal to just x, right, the x bar, right, because this is a term quotient, so this is already defined for us, and c to the m is equal to c bar, and f of m of t1 tn is equal to f of t1 tn bar. This is well defined because it is a quotient, no, because it is a congruence. And finally, for relations, we have r of m of t1 tn if and only if y are t1 through tn. Okay, this is because we showed that if this is well defined because we showed that if t1 is equal to t2 1 prime through tn is equal to tn prime, and y says that r t1 through tn, and then that means that y here, if y says all this, then y also says that r of t1 prime through tn prime. Okay, so this is all well defined. By term induction, t to the m, the interpretation of t is just the quotient class of t for all terms. Notice that by H3, every term is going to be congruent to some constant, right? Because by H3, what is H3? H3 says that for all terms there exists a C that X says that T is equal to C. So that literally says that T is congruent to C. So A is going to equal all the congruence classes of T for T terms, which is just going to be all the congruence classes of constants for C constant. Okay. And now we want to show that M satisfies alpha if and only if Y implies alpha. For prime formulas, negations, and conjunctions, this is clear. Now for quantified formulas, we have M if and only for all x alpha, if and only if M C bar x satisfies alpha for all C constants, which is if and only if M of Cm x implies alpha, because C bar is equal to Cm, which is if and only if M satisfies alpha C over x by the substitution theorem, which is if and only if M satisfies for all x, which is if and only if Y satisfies alpha C over x, alpha implies by induction, which is if and only if y satisfies for all x alpha, since this holds, right, because by h2. Sorry, this is just by h2. Okay, so this is by h2, right, because h2 literally says that x implies for all x alpha if and only if x implies alpha of c over x for all c. Okay, and so what we get is every Henkin set is satisfiable, so we get theorem, the following theorem. We have completeness, we have finiteness, and we have compactness. So what we just showed is that so the same thing as in predicate as propositional logic is x satisfies alpha if and only if x is x, but both of these derivability relations are equal. Finiteness says that x satisfies alpha if and only if x not satisfies alpha, not satisfies, but it's derivable from alpha for some finite x naught. And finally, compactness, x is satisfiable if and only if every finite subset of x is. Okay, same thing as in propositional logic. Okay. Now let's talk quickly, now for our last 7 minutes, let's quickly talk about theories, definition. A theory is a set of sentences which is deductively closed, i.e. T implies alpha for alpha sentence, for a sentence alpha, if and only if alpha is in T. Okay. Sorry, let's write this a little clearer. Okay, and so if I'm talking about a set of sentences, and I say the theory S, what I really mean is I mean the theory of the deductive closure of S, which is all alpha sentences such that alpha is derivable from S. Yeah. So this is a theory. This is a theory, because if S prime satisfy, if S, the deductive closure of S satisfy, it's derivable phi. That means that since S, so we have S derives S phi, S as the deductive closure, which derives phi. We get that S derives phi, so phi is in the deductive closure. And furthermore, if A is an L structure, its theory, the theory of A, is all the formula, not the formulas, but all the sentences such that A satisfies phi. And this is also similarly a theory. No, this is weakly. Okay. Okay. Now, so let's say, for example, that, let's say, for example, let's look at N with the signature, with a signature, let's look at n with a signature containing less than, plus, and 1. So it has a relation, a binary relation. These are all interpreted canonically. Okay. So now what I'm going to say is that there exists a model of the theory of n which is not isomorphic to n. Okay, so basically what this means is that there's a non-standard model of the theory of n, right? Something that's equivalent to n, but it's not isomorphic to it. It doesn't matter what you add to the signature, you're still going to have this. Now the reason for this is let's define our set of sentences x to be the theory of n, or and the union of x is greater than n for all n in n, where x is greater than n is defined to be x is greater than 1 plus 1 plus blah 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 plus 1. Right, so this is a formula. This here is a formula in L. Right, so I guess what I mean to say is this is in L. Okay. Okay, now we claim that x is satisfiable. And if x is satisfiable, then there's something that satisfies the theory of n, and it has an element that's greater than every natural number. Now what this would mean is that we have something that is a model of the theory of n, sure, which is what we want, but it's also not isomorphic to n because we can't map anything to x, or we can't map x to anything, because it wouldn't preserve the order. Okay, take a finite subset of x, let's call it delta, and so delta is going to be a subset of the theory of n, and x is greater than n1 through x is greater than nk for some n1 through nk. And this is obviously going to be satisfiable because I can just take, n satisfies delta where x is interpreted as the maximum between n1 and nk plus 1, right? And so n satisfies delta, and that means that this set of formulas x is satisfiable. So we have some model m which satisfies x, and the domain of m is going to be some set, or the structure in m is going to be some set with this x in it, which is greater than every natural number. And so it's not going to be isomorphic to the natural numbers. Okay. And that's going to be it for this week. We did pretty much everything that I wanted to. So that's great. We're at good pace. If there are any questions, now's the time to ask. And by the way, I'm using OneNote. Of course. Thank you guys for coming. Oh, and by the way, about this, so about this problem set. So this problem set is going to be a harder problem set. It's going to involve some algebra and topology. So if you guys don't know algebra or topology, that's totally fine. Just don't do the questions regarding algebra and topology. So just a heads up. And so also today I will be posting the solutions for the second problem set. I will hopefully be able to upload the third problem set if I'm able to finish it, and I'll upload this week's lecture notes. Of course, thanks all for coming.